So thank you very much. So controlling fluid flows means acting on them in order to reach a specified target. So, but imagine we can ask, so how effective can be apply fluid flow control techniques in everyday processes and the benefits that we have in doing so. A list of targets that we can have for the application of fluid flow control techniques is represented here in the slide. The most important, so the one that received great attention in the recent years is drug reduction. And in order to comprehend how effective is applying this technique to, with this target, we can make an easy example, so an everyday life example. It's the case of the automotive sector. So a large portion of CO2 emission in this case is due to the aerodynamic drag. So imagine of driving a car at 50 kilometers per hour, the aerodynamic drag accounts for 50% of the total resistance of the vehicle. And while moving to 130 kilometers per hour, it accounts also to 80% of the total resistance. Some results have proved to be effective in this way because we can reach a 25% drag reduction in this sense. And that means also consuming less CO2, so producing less CO2 in the, and specifically 2 kilos every 100 kilometers. So we are producing less CO2 in this case. Well, fluid flow control techniques can be applied to other different fluid flow related industrial processes. It's the case of the aeronautical field. Here we have an example from Puri et al. In which the separation control is performed by putting jets at a specific position of the airfoil in order to control the separation, so to achieve a lift enhancement and also a drag reduction in condition of high angle of attack. So among the control strategy that we can consider in this case, the active flow control is the one that received much attention because of its performance. And this is to what my PhD thesis is focused. So trying to apply a specific control technique that is called model predictive control for fluid flows. The PhD thesis is supervised by Professor Stefano Discetti and Andrea Melambila. And talking about active flow control, it means including power of actuation, but also a control strategy that is the way we select the control action. So model predictive control is the focus of my thesis. So when talking about this control strategy, I really like to perform a comparison with the game of chess. A good player, when playing chess, in order to win the match, tries to predict as much as possible the steps of the game into the future before moving a single action, which is moving a single piece on the chessboard. And for step of the game, I mean the opponent's move and the player's move, so the player actions. So the selection of the action here is a result of a prediction optimization algorithm. And this is how also the model predictive control is working. So here we have a schematic of the control. It belongs to the reactive flow control because the control optimizer, in order to select input to control the system plant, is is informed by a partial or total measurement of the system plant state, of the plant state. So we want to control, so to select the input, this is done by the control optimizer in order to make the system plant follow a certain reference. So what happens inside the control optimizer is to make use of a system of the model, in this case our fluids, in order to perform prediction of the state dynamics, starting from a specified time step of the control where a measurement of the state is available. The prediction of the state are useful for run an optimization problem that is able to, which output is basically a control strategy defined into the prediction window. And that's also why after the optimization problem has been performed, so the control applies only the first component of the optimal control sequence, and then the procedure is repeated at the next time step of the control. This is also why model predictive control has been widely recognized as an optimal control strategy over a receding horizon, in which constraint can be easily taken into account because the output selection is made up by an optimization problem. What is difficult in applying model predictive control to fluid flows is generally have a model of the plant. Actually, well, we have a model of the plant, but they are Navier-Stokes equations. So imagine putting Navier-Stokes equation here inside the control optimizer, in which an optimization problem is performed at a certain frequency, depending on the time step of the control, on the time step of the control. So this will make the control unfeasible because of the computational cost. So what we need is to create a model of the system which is reduced. So it's a reduced order model of the system, and it's selected by performing a trade-off between the accuracy and the computational cost. Well, this is really difficult to do in fluid flows because obtaining such a model is challenged by the behavior of fluids, which is generally chaotic and characterized also by strong nonlinearities. Nonetheless, some data-driven techniques and machine learning techniques advancements in these fields are providing more and more techniques in order to obtain models from the plant. And this is the focus of the PhD thesis. So try to overcome these difficulties in the selection of the model, and also focusing on the applicability of model predictive control when there is noise in this line of feedback and there are uncertainties in the plant. So this is a summary of the literature research what I have done during the first year of PhD. So first of all, there is a literature review of the existent approaches in fluid flows, and this is really scarce. So there are not many applications of model predictive control for fluid flows. Anyway, since we want to apply the model predictive control because it's really promising in this field, we have to face two different problems. The first one is related to the model predictive control itself, so the algorithm of the control, but also some methods in order to automatically select the parameters of the control. And the other one is related to nonlinear system identification because we need to create model of the plant. And there are different trends in this case. The first one is obtaining an analytical model from data, as the group of Brandt et al. Is doing with the sparse identification of nonlinear dynamics. And the other one is performing prediction by performing a time series analysis. And it's the case of the NARCS method, so nonlinear autoregressive exogenous model, in which to perform prediction, we can also include some methods like the deep learning. And this is the research that we are planning to do during this 3 years of PhD. The first year has been mainly focused on literature research and exploring also new methods, mathematical and statistics, in order to handle noise and model uncertainties in the plant. So to understand the effects of this noise and model uncertainties and trying to overcome them. And testing of the MPC in simple test case in fluid dynamics, like the chaotic wake of the fluidic pinball. Some results are presented here at the right part of the slide. And also, by the end of this year, we're going to provide some experimental tests, some experimental proofs of that method is working basically on fluid flows. Second and third year will be mainly related to the application of model predictive control to more complex cases like turbulent ones or lab scale problems, so real world problems. This is a list of the conferences I have attended so far, and also some others I have been accepting and where I will present my work. We are going also to publish an article based on the preliminary result that we have on the control of the fluidic pinball and in its laminar chaotic behavior. And that's all from my side. Thank you everyone for the attention.